Okay. So now that we have been we were able to discuss now yung root locus ninyo. Okay. We will now be able to use this tool as a means of coming up with a controller design para ma-meet natin yung transient response and steady state error requirements while we ensure that the system is stable. Okay. So in the previous lesson, okay, nakita natin that we can actually come up with a design, with a decent design of your controller. Kaya lang, since we are just merely adjusting the gain, okay, it also means that we are only working along the root locus only. Okay, and therefore, our improvement would be limited to those points that are on the root locus. Okay, but then if we would want some more flexibility. Okay, if we would like to be more flexible, okay, in terms of meeting your requirements. Okay, um, both in terms of transient response and steady state error, then we would need to be able to reshape. Okay, there is a requirement for us to be able to reshape the root locus, uh, and that is accomplished by adding poles and zeros to the system. Okay, so this chapter will demonstrate how are we able to do this. Okay, how are we able to design these compensators so that we can meet these requirements. So yung made-design nating yung made-design nating compensators or controllers, okay, are basically either passive controllers or active controllers. Okay, so remember lang na when we talking about your system, again, yung ating general topology would be something like this one. Okay, so yan. Okay, so this is your input R, this is your output, say Y. Okay, now this is your F, your input transducer F. This is your plant G. Okay, this is your feedback H. And this would be your controller C. Ito yung i-design natin. Okay, we would need to come up with a design of the transfer function for this C so that we would be able to meet your transfer function, your transient response and steady state error characteristics. Okay. Now, there are two ways to design this controller. So yung una nga is yung we will be using passive networks to do this. Okay, or we will be using active networks. Okay, so basically sa konteksto ng pinag-aaralan natin, itong C na to is basically itong controller natin to is basically an electrical network. This would eventually boil down to an electrical network. Okay, so dahil nga yung H natin would be the sensor, F would be a converter that would convert the input to an electrical signal, and our G is basically your plant or your process, okay, which may be mechanical, okay, or electromechanical or pneumatic or whatever system, okay. So yung C natin is basically an electronic circuit. Ang controller natin or ang compensator natin is an electronic circuit, okay, which can either be passive or active. Okay. Now, dalawa yung approach na gagawin natin dito. Okay. So kapag active, okay, we'll be coming up with a what we call a proportional integral derivative controller or compensator para sa ating controller. Okay. So yung itong PID controller natin would be using active circuits. It means it would be implemented using an op-amp. Okay. So ayan. Now, if your controller naman is chosen to be passive, it would be a lead lag circuit, okay, which would comprise mostly of it would just mostly be composed of passive networks. Okay? So, yun yung tinitingnan natin dito. Okay? So, at the end of this lesson, you must be able to use the root locus to design cascade compensators to improve the steady state error. Okay, use the root locus to design cascade compensators to improve the transient response. Use the root locus to design cascade compensators to improve both the steady state error and the transient response, and to realize the design compensators physically. Okay, so that. Now, the root locus would typically allow us to choose the proper loop gain, okay, to meet a transient response specification. Okay, so as we ayun nga, the root locus would allow us to meet a transient response specification. Okay, so adjusting your gain along the root locus would give you the proper gain para makuha nyo yung tamang transient response na gusto natin. Okay. However, setting the gain at a particular value yields a transient response dictated by the poles at that point on the root locus. Okay? So, kung gusto nating i-set yung ating transient response sa ibang parte ng ating S-plane, okay? O sa ibang we would be only limited, we would not be able to do that, na mai-set natin yung ating operating point, or may set natin yung ating closed loop poles sa isang point na wala dun sa root locus. So therefore, limited lang tayo dun sa root locus natin mismo. Okay? So, for example, kung titingnan natin tong ating improvement in the transient response. Okay, we will have the following. Or we can see the following. Okay. Halimbawa, may gusto tayong i-meet, say for example, settling time, okay, or peak time. Okay. Now, if your pole, okay, or if at a certain gain, okay, nandito yung location ng pole niyo. Okay, if at a certain value of gain, nandito yung location ng pole niyo. Okay, remember lang na yung close to pole niyo. Okay, remember lang that you would only be limited by you would only be limited in setting your gain along this root locus. Okay, so halimbawa ngayon na gusto niyo ngayong say for example, mag-meet ng certain TS or TP requirement yung inyong system. Okay? Then you would be changing your overshoot. Kasi magbabago this line actually sets that or along this line your overshoot is constant, or your overshoot is essentially constant. Okay? Pero once na gusto niyo, say for example, i-meet yung TS or TP, take note that TS is basically 4 over sigma t, or the real part of your pole, or of your closed loop pole, and TP is basically pi over the imaginary part of your pole. So kung iibahin nyo either TS or TP, take note na iibahin nyo yung real part or imaginary part ng pole niyo. Okay, so that means you either move towards here o kaya towards here. Okay, and if you see na we would just be moving along this root locus, then definitely may iba yung location ng the outline niyo. Okay, now what if we want to meet a certain TS or TP requirement, but at the same time we want to make our overshoot essentially the same, okay, with the original uncompensated system. Okay, so kung wala pang compensation or hindi pa natin na-design yung compensator na system niyo, it has a certain overshoot. Then kapag nagkaroon na siya ng compensator, mamimit natin yung TS, and at the same time mapapanatili natin na constant yung yung overshoot niyo. Okay, that would require you to move your pole from here to here. Okay, to a point somewhere here. Okay, which now, obviously, wala na sa root locus natin. Okay? So therefore, kapag ganyan yung pag ganyan yung kailangan nyo, okay? Yan, for example, kung titingnan nyo to, in this case, there is an improvement in TS kasi ito yung TS nung sa A. Pero yung sa B, okay, nandito yung TS niyan. So nag-improve yung TS niyan, bumilis yung settling time. Okay, pero makikita nyo na yung kanyang overshoot, halos pareho lang. Okay, it is possible by moving from point A to point B. Okay, but again, as you can see, point B is not on the root locus. Okay, so paano natin ngayon mamimit yung ganung requirements that we improve TS but at the same time we maintain the overshoot. Okay, so in that case, what we will do is we would need to have your root locus reshape. Kailangan mabago natin yung shape ng root locus natin. And then, when we reshape your root locus, we will make that root locus pass through that point B. Okay, so hindi lang basta reshape. Pag ni-reshape natin siya, dapat yung root locus nyo dumaan din sa yung bago yung root locus na ni-reshape no, dumaan sa point B. Okay? And how do we do that? Okay, how do we reshape the root locus and then make the root locus pass through a certain point? Okay. By the way, tatawagin natin tong point B as the new operating point. Okay, and itong point A as the old operating point. Okay. So instead na actually we can also call that as the complex dominant pole. Pero para mas suggestive siya or para mas intuitive siya, okay, we will call those operating points where your system is said to be operating on. Okay. So basically that's the closed loop pole that your system operates on. So that mamimit niya ang certain, say for example, overshoot or certain damping ratio. Okay. And then i-redesign natin yung controller natin such that yung operating point na yan, magagalaw natin into a new operating point that would meet our requirements. Okay? So, how do we then, babalik tayo sa question natin. How do we then move or how do we then reshape this root locus and at the same time, make the root locus pass through a new operating point? Okay? So, what we do is we augment. Okay? We augment or compensate the system with additional poles and zeros. Okay? So what we will do is we will add open loop poles and open loop zeros sa ating system. Okay? So yung open loop poles at saka open loop zeros na yun, doon manggagaling yun sa controller natin. Basically yung controller nyo, okay? Say for example, you have yung transfer function ng controller nyo, aside from the gain, meron din siyang compensator zero at saka compensator pole. Okay? So, ayan, idadagdag natin to dun sa, ito yung controller niyo. Yan yung multiply dun sa G, which itself has its own open loop poles and open loop zero. So, yung compensator zero tsaka compensator pole natin would actually augment yung open loop poles and zeros ng G. Okay? Which in turn would actually reshape your root locus. And would actually force your root locus to pass through a certain operating point that we desire. Okay? So, yun yung approach na gagawin natin to be able to improve the transient response and the transient response. Okay? So there. Now, how about the steady state error? Ang steady state error basically isang way of actually improving your steady state error is increasing the system type. Okay? Take note na halimbawa, if your system is a type 0 system, okay? So halimbawa meron kang K over S plus 1 times S plus 2. Okay? If you have this system na type 0, okay? So alam natin na meron yang error sa step input. Okay? So kung gusto nating ma-zero yung ating system or yung error natin or yung steady state error natin due to a step input, what we want to do is to increase the system type of this. gusto natin siyang gawing type 1 para magkaroon siya ng integration factor dito. And thus, ito, magiging 0. Kasi yung kanyang Kp, okay, mag-i-increase yan up to infinity. Okay? So, yung improvement na yun, okay, can actually be done by adding an integration factor doon sa inyong forward transfer function. So ito, ang mangyayari ngayon dyan is that yung ating controller, meron na siyang gain, tapos meron pa siyang integrator. Okay? Tapos ito ngayon yung g ninyo is 1 over s plus 1 times s plus 2. Okay, which would be your forward transfer function. So from there, makita natin na yung system type niyo mag-i-increase from type 0 papuntang type 1. And therefore, that would render your steady state error to a step input to be 0. Okay? Also, kung hindi naman siya 0, okay, kung hindi naman siya 0, I mean, hindi naman natin talaga target na maging 0 ito, pero we just want to have some kind of improvement. Okay? Ang tandaan lang natin is that we want to increase Kp. Okay? When you increase Kp by a certain, or your static error constant in general, by a certain factor, you would be able to see na magkakaroon din ng dramatic decrease sa error. Okay? Take note na ang ating error due to the step input is basically 1 over, or A over 1 plus Kp. So that kapag in-increase natin si Kp, alam natin bababa si steady state error. Okay? So that would be accomplished. Okay? That can be accomplished by adding A0, okay, and a compensator pole. Okay, dun sa ating controller. Okay? And then making sure na yung ratio ng ZC over PC. Okay, yung ratio na to. Okay, yung ratio ng ZC over PC would actually be greater than 1. Kasi kapag kinumpute natin yung error, or kinumpute natin yung, say for example, meron na tayong forward transfer function na K times, say, S plus CZ, okay, over S plus PC times S plus 1 times S plus 2. Okay. Pag kinumpute nyo yung, pag kinumpute nyo yung KP nito, okay, pag kinumpute nyo yung KP niya, that basically is K times CC over PC times 1 times 2. Okay? So kung yung ratio na CC over PC natin is actually greater than 1, then we can expect an improvement in KP and therefore an improvement in the steady state error performance of your system. Now, what's a good thing is that makokontrol natin kung nasan tong ZC at saka PC natin, so that hindi lang natin siya may state as greater than 1. But actually, we can actually set yung value na yan. Itong value na to. For example, kung gusto natin ng 10-fold improvement in terms of the steady state error, or in terms of the static error constant, then we can set CC over PC to be equal to 10. Kung gusto natin ng 10-fold reduction, 10-fold improvement in the static error constant. Okay? So kung 10 yung isa-set natin para dyan, then we can choose a location for your compensator 0 at saka compensator pole para maging 10 yung ratio na yan. And therefore, pag kinumpute natin yung KP, there would be a 10 times improvement in the KP. Okay? And of course, in terms ng KP at saka ng steady state error for the step input, hindi kasi exactly sila proportional dahil merong 1 na factor dito. Okay? So, parang halimbawa, in terms of unit step, yung 10 times improvement sa KP would actually translate to around 1 over 11 na reduction sa error. Okay? So, hindi sila exactly proportional. I mean, proportional sila pero hindi sila exactly parehong value. Hindi katulad niyan na kapag KV at saka yung steady state error due to ramp, kung ito i-improve mo by 10 times, mag-reduce din to ng 10 times. Okay? Kasi sila, yung formula nila is basically ang ating steady state error due to the ramp input is basically 1 over kb. So pag ito in-increase mo by 10, ito magde-decrease by 10. Okay. Same thing with the parabolic boot and the KA. Okay, pero sa KP kasi iba yung usapan dahil merong extrang 1 na factor doon. Okay, pero more or less medyo mape-predict natin na pag tinaas mo si KP, bababa si error. Okay? So, that is how we improve the steady state error. That is, either we introduce integration factor so that we can reduce the error to 0, o kaya we can introduce poles and zeros, okay, or compensator poles and zeros para makita natin na ma-achieve natin yung improvement sa static error constant na kailangan natin. So yung mga yon, yung mga techniques na yon will actually be discussed in the next sections. Okay, nung ating chapter na to. Okay. Now, so as I was saying kanina, okay. Yung configuration, mahalaga na magkasundo tayo dun sa configuration nung ating system na gustong i-compensate. Okay? So actually merong various techniques of doing of compensation techniques, okay, na available. Yung isa is yung cascade compensation na tinatawag, okay, in which yung compensator ninyo is basically naka-cascade or naka-series dun sa ating plant. Okay. The other one is that tinatawag na feedback compensation, okay, in which yung compensator ninyo is ilalagay natin dun sa feedback. Okay, sa feedback loop. Okay. With cascade compensation, the compensating network, okay, is placed at the low power end of the forward path in cascade with the plant. Okay, so that is why yung compensator mo actually requires a low power or it has low power requirements. Okay, kasi yung compensator mo hindi mo nilalagay dun sa pwesto nung or dun sa part nung system mo that actually requires high power na, for example, nire-require nung system ng plant mo such as motor, okay, or a hydraulic system na mataas yung power. So ilalagay natin siya dun sa low end power nung system natin. Okay, that is why we will design this controllers using electronic circuits. Kasi nga hindi naman malaki yung requirement nila pagdating sa power. Okay, ang kailangan na nila is magbato ng signal dun sa inyong plant. Okay, in which that signal would actually cause your plant to react in a certain manner. Okay, and therefore would be responding to that signal. Okay, depende dun sa level niya. Okay, depende dun sa level ng signal na yun na ibabato dun sa plant natin. Okay, now in this lesson, okay, we will be limiting ourselves to cascade compensation techniques. Okay, so limited lang tayo dun sa cascade compensation techniques. Okay, and again, paulit-ulit ko na sinasabi sa inyo ito, yung tungkol sa topology na gagamitin natin. So again, we will be using yung topology na pinakita ko sa inyo before pa, okay, in which ang i-design natin doon is yung compensator na nasa tabi ng ating plant. Okay? Now, compensators. Compensators that use pure integration for improving steady state error or pure differentiation for improving transient response are defined as ideal compensators. Okay, so pwede natin gamitin yung ating pure integrator, okay, or yung ating integrator at yung ating differentiator, okay, to be able to improve steady state error para sa integration or integrator at saka transient response para sa differentiator. Okay. But these compensators are only implemented using active networks. Okay. Yung ating integrator, okay, yung 1 over S natin na system, at saka yung ating differentiator, okay, yan ay i-implement lang in circuit, okay, using active networks. So, ma-implement lang natin yan using op-amps. Okay? So, other design techniques that preclude the use of active devices for compensation can be adopted. Okay, these compensators, which can be implemented with passive elements such as resistors and capacitors, do not use pure integration and differentiation and are not ideal compensators. So, meron tayong, pwede naman nating i-implement yung ating compensators using passive elements such as resistors and capacitors. Okay, and which those would not require active elements. Okay, such as op-amp. Okay, and therefore does not also require its own power supply. Okay, so the choice between an active or passive compensator revolve around cost, weight, desired performance, transfer function, and the interface between the compensator and other hardware. So yan yung ating design consideration kapag mamimili kayo kung active or passive compensators ba yung nire-require ng system niya. Okay?